Hi everybody. In this very short video lesson, I'm going to show you how to get started with some of the questions on the worksheet. The worksheet is about the law of universal gravitation, and we discovered in class that the law of universal gravitation states that whenever you have two masses, they're going to attract each other with a force F, and that's a gravitational force. In class, we discovered that force is directly proportional to the product of the masses. So the m1 times m2. And we also discovered that the force is inversely proportional to the square of the distance between the masses. And so this is a famous example of an inverse square law, because the force gets smaller as the distance grows by an inverse square. So in this activity, you will assume that the force of the gravitational attraction between two identical asteroids equals F when they are separated by the distance shown. Use the law of universal gravitation to predict the forces of attraction in the other cases. So this very first case is our reference, and I'm going to write that next to it. So if you have asteroids with masses 1 and 1 separated by this distance, then they're going to attract each other with a force F and F. So remember, these forces are equal and opposite. So this reference case basically is going to be, the product of masses is 1. We're going to say that the distance squared is 1, and the force is going to be equal to F. Okay, let's go to the next case, the first case that I want you to figure out. So what if you have a mass of 2 and a mass of 3, and they're separated by that same distance? So what you do with this is, first of all, you take the product m1, m2. And so we would say 2 times 3. Okay? And that's equal to 6. All right, that's the product of masses. Now, on the distance, in the distance column, if we're keeping track of distance, there's no change in the distance compared to the reference, right? Because this distance and this distance, they're the same. And so that would just be 1 squared, which is equal to 1. And so my force here, F, is going to be equal to 6F over 1, which is just 6F. And so what that means is that this force of attraction is going to be 6 times stronger than the original. This is my answer, okay? I can't even draw that in this picture because I'd have to draw the arrows 6 times longer, and I don't have space. So this is a much, much stronger force, and that's because we have more masses here, right? If you double one mass and triple the other, it gets bigger. So that's the kind of thing that what we mean. Let's do another example where we change the distance, okay? So let's take a look maybe at this one. So if you look here, you'd see, well, my masses are back to 1 and 1. So if I'm keeping track of masses, I have 1 times 1, that's equal to 1. And that's the same as my reference case. Now, on the distance score, my distance here is going to be twice as great as the distance in my reference. So I'm comparing this distance to the reference distance, okay? And that's a doubling. So this is going to be 2 squared is equal to 4. And so my force in this case, the force of attraction between these masses, is going to be 1 F divided by the distance squared, 4. And that, of course, is just equal to 1/4 F. Okay? So if you think about it, when you move the masses, farther apart, the force gets weaker. That's a very common sense idea, right? The further apart they are, the weaker it gets. And by doubling the distance, you're actually making the force 1/4 as much. Okay? And we're figuring that out by keeping track of these factors, right? Mass, distance squared, and we put them together in the last column. Let's do one other example where you got both things changing in the same case. Let's pick, for example, this one. Okay? So if you have 2 and 4, the product of masses is going to be 2 times 4. That's equal to 8. So looking at mass alone, you would expect the force to be 8 times stronger. However, if you look at distance, you've got 1, 2, 3 3 times the original distance. If I square that, that's going to be 9. So the force of attraction between these objects is actually going to be given by 8/9 times the original force. And that force is actually a little bit weaker than the reference force, because 8/9 is slightly less than 1. Excuse me. And so even though the masses are much greater, the fact that you've tripled the distance really, really affects the force and knocks it down. So that's kind of how you do the problems on this side. It's okay if you express your answers as fractions here. It's probably the simplest thing to do. You don't need to convert them into decimals. But basically, you're always converting something and multiplying it by f so that you can compare it to your original reference case. So go ahead and try those out and see how you do with the rest of those. I am going to flip over to the other side. And the problems on side 2 are kind of a word problem version of what you just did. Okay. So let's take a look at one of these. The instructions say to solve for the interaction force in each case below using the proportionalities given by the law of universal gravitation. I am going to write that law here. Okay. That sign, by the way, is a proportional sign. It looks like a fish or an alpha, and it simply means that the force is proportional to the stuff that's over here, the product of masses, the inverse square. I do not write an equal sign here because I would need a constant to go in to make these equal, and we're going to worry about that tomorrow in class. Okay. All right, so in the first case, we've got the two masses here attracting each other with a force F. It's telling us that that force is 12 newtons. Okay, so they're attracting each other with a force of 12 newtons. So what's the force going to be in the bottom case? So the way that you can approach this is the same way that we did the other side of this worksheet. You can look at the masses first. And you can say in the second case, the mass factor is going to be 2 times 3. That's your product of masses. Of course, that's equal to 6. Then you can look at the distance factor. We've got 1, 2, 3. Right? So the distance has been tripled. So if I square my distance, I get a factor of 9. And so the force I'm going to end up with here is going to be, according to the law of gravitation, 6/9 times F, where F is one of those forces that we started with. And the difference here is that we know that F is equal to 12 newtons, and so this is equal to 6/9 times 12 newtons. And of course that's 2/3. 6/9 is 2/3, and 2/3 of 12 would be 8 newtons. And that's the answer. Okay. So with these problems, what you're doing is that the main difference is that I'm giving you an actual value for the reference force, and you're using that to figure out the force in the cases that are underneath. Okay. So that's how you do the rest of these cases. By the way, this is supposed to be a 10 in that case. You might not be able to tell that. And I think if you go further down, this is kind of awkward. This is supposed to be 2.5. Right. Okay. So that's how you handle some of those other cases. Also, be really careful sometimes in some of these problems. Your reference distance would be this distance here. Oh, sorry, that's not the one I wanted to use. I was going to say, if you look at a case like this, you've got a reference distance that's that big. In a case like this, your reference distance is half as much. So, hint, hint, when you do the distance factor here, it's going to be 1/2 squared, which is equal to 1/4. And you're going to have to divide by that, right? Something over 1/4 times force to get your answer, right? And then the mass part goes on the top. So this is a little bit tricky because you're moving the objects closer together, And when you do that, the force gets stronger. So you should be dividing by the fraction 1/4. All right, I think that's enough of a hint. So tonight, please finish up both sides of this worksheet, all the way down to the bottom, and we'll check in on Wednesday.